everyone. Welcome to the fourth talk in Bose colloquium series on quantum materials and devices. Today we have a talk by Professor R.P. Singh. Uh, so most of you know him, but as a formality, I'll introduce him. Professor Rajiv Singh is one of the renowned condensed matter theorists at the Department of Physics and Astronomy at UC Davis, USA. His research activity involves using statistical mechanics and computational method to study a variety of problems in theoretical physics. These ranges from electronic behavior of solid to protein structure and noble mechanism in biological physics. Professor Singh has contributed immensely in understanding of various noble phenomena in magnetism and superconductivity, and developed and studied various statistical models that exhibits exotic and novel paradigm of cooperative many-body behaviors. And examples are like novel quantum phases, quantum phase transitions, novel excitations, and novel mechanism of order and disorder system. In biological physics, he has also contributed significantly in understanding of conductivity of DNA and protein misfolding aggregation inside cell, which leads to various diseases. He is a fellow of many societies. Some of those are like fellow of Institute of Physics, fellow of American Physical Society, etc. Got many awards. And with this, I'll request Professor Singh to give the colloquium.
Okay, well, thank you, Manoranjan. When I was invited to give this talk, I felt very honored, and I really thought back to the first time I visited the Bose Institute, which was probably before many of you became members of this institute. The year was 1994, and that was the centenary year of Bose. And there were two major conferences held in Calcutta that year, separated by about 2 weeks. One of them was organized by the government of India, and I remember Tony Leggett was one of the speakers, and perhaps David Gross was another speaker there. The other one was a smaller meeting organized by the Bose Institute, where I was one of the speakers, and Professor A.N. Mitra, who was my former teacher at Delhi University, he was the plenary keynote speaker who gave a really inspiring talk about Bose and his lifelong association with Albert Einstein. Very, very inspiring talk. And I thought this would be a great opportunity for me to pay my tributes to S.N. Bose, whose impact really is all around us in quantum mechanics and in condensed matter physics. And so I thought it would be nice to say something about Bose condensation phenomena in magnetic materials, which I mostly work on. And also, I thought would be a good opportunity to pay my tribute to Chanchal Majumdar, who was the founding director of the S.N. Bose Institute. And actually his very early work on quantum magnetism, on an exactly soluble model of frustrated quantum magnets, really sets the stage for where post-condensation becomes important in these magnetic systems. So thank you for the opportunity to give a talk here. Okay, next slide, please. I'm sorry, I don't have control over the slides myself, since I was not able to share the screen from here. Okay, thank you. So basically the outline for my talk is going to be as follows. I'd like to begin with a general motivation to the subject of quantum magnetism, and in some sense, the most important subject in that field, or the holy grail of the field, which is really quantum spin liquids. So I'd like to begin with a general motivation and introduction to that subject, and then talk briefly about frustrated rare earth magnets. I'm really not an expert as such in rare earths themselves. I'm more of an expert in magnetic systems. So my discussion would be more by illustrative examples. Okay, so first a discussion of spin ice, and then a few particular topics that my research has been in. And in particular, we had a recent FISREV letter on this subject of Bose-Einstein condensation in this particular rare earth material. So I'd like to discuss that and then end up with summary and conclusions. And my main collaborators in this, basically, Jan Oitma from University of New South Wales is really my long-term collaborator, and Michelle Jingra from University of Waterloo. And then there are two of my students, Aniruddha Menon and Michael Flynn, who have both graduated and are postdocs now, and Tom Baker, who used to be at Sherbrooke at the time. So next slide, please. If I point towards something, people probably cannot see the arrow of my screen. Is that correct? I would
Yes.
guess that. Okay. All right. So yeah. Okay. All right. So I'm going to begin with this general question, really, of what is a quantum spin liquid. I'm going to assume that this is a broad audience, really, and I'm trying to define what a quantum spin liquid is. And this name really is derived from the ordinary phases of matter that we are very familiar with, the phases of matter associated with atomic motion and arrangement. We are all familiar with this phase diagram of water, which has the solid, liquid, and the gas phases. And if we think about these phases, really, the phases arise as a competition between enthalpy and entropy, as we learn in statistical mechanics. Entropy basically favors more randomness, more disorders, and it naturally favors a gaseous phase. Enthalpy favors more ordered systems with lower energy, and that favors a solid state. So in some sense, both solid and gas phases are relatively simple, and we have very nice model that we can teach at the undergraduate level about models of gases and solids. Whereas the liquid phase is actually a much more complex phase in the sense that it is a condensed phase where atoms are interacting strongly. They essentially have the same density as a solid, very close, and yet it's a fluid phase. So the liquid phase is much more complex, much more interesting, and of course it sustains life and does all kinds of very interesting things. So it's much harder to model, and of course we are interested in something similar in context of spin. So next slide, please. Okay, so of course, but that liquid phase exists for, say, most materials exists only between the critical temperature, above which, again, there is no liquid phase, and a triple point, just slightly below the triple point, below which, again, there's no liquid phase. So the liquid phase that we are familiar with typically exists over a very small window. A quantum liquid would be one that exists all the way down to zero temperature. And the only material that at ordinary conditions, at ordinary pressure, at atmospheric pressure, remains a liquid all the way down to zero temperature is helium. And the phase diagram of helium is shown on the right. Basically, the critical temperature is at something like 5.2 Kelvin, really, and just a few at 1 point something atmosphere. And really, one needs to put something like 27 or so atmospheres of pressure in order to solidify helium even at zero temperature. So it remains a liquid, and in fact it turns a superfluid, which itself is a kind of Bose condensate. So it's a liquid that shows macroscopic quantum behavior. Okay, so that's basically what I'm looking for. What we are looking for in context of spins, as I'll discuss on the next slide. So the reason why helium is important. Okay, sorry, can you just go back for 1 minute? Yeah, so, and the reason why, we all know the reason why helium has this behavior and others do not. The two key properties are that the helium is inert. It's one of these noble gases which have very weak interaction, so that really there's not much to be gained by going to an ordered phase. And it's the lightest of all the noble gases. And lightness means that there's much more quantum fluctuation there. And that's the reason why it stays a liquid all the way down to zero temperature. Okay, next slide, please. Okay, so now what is a quantum spin liquid? Well, the idea now is we are no longer interested in the atomic motion and arrangement, basically. We assume that we have a system, we have a solid system where atoms are all perfectly arranged, and the only interesting degrees of freedom are really spin orientation. Okay, so they contain atomic spins or there's some atomic angular momentum associated with them, and we are really interested in the fluidity associated with that spin orientation. So in analogy with the discussion for ordinary phases that we are familiar with, we would say that spins basically solidify at low temperature into crystalline structures. They either form antiferromagnets where they all line up parallel to each other, or they form an antiferromagnet where neighbors align anti-parallel with each other. So those are like crystalline arrangements. Again, they are simple phases. We can easily develop a simple theory for them. Maybe not at the undergraduate level, but certainly at the graduate level, those are taught. And then again, at high temperatures, basically the spins, they fluctuate. Each spin fluctuates independently. That's like a gas phase, and that's a paramagnet in the magnetic language. So both the solid phase and the gas phase are well described. A phase in between which has all the short range order and yet continues to fluctuate would be called a liquid. So under what conditions can we have a spin liquid? And in particular, can they form a quantum spin liquid? Can that behavior extend all the way down to zero temperature? Okay, next slide, please. Okay, so the two properties that we discussed which made helium into a quantum liquid basically were inertness and lightness. In context of magnetism, these two properties basically translate into geometric frustration and low spin. So geometric frustration can be illustrated by thinking about a triangle. Let's say, imagine having spins on the vertices of a triangle, and suppose the spins interactions are such that they like to align anti-parallel, then it's clear that the third spin doesn't know which way to align. And what happens in such a system is that lots of configurations have essentially the same energy. Okay? In this particular example, if we think of Ising spins, which can take values plus or minus 1, basically 6 out of the 8 spin configurations have the lowest energy. So there's no real selection from the energetic point of view. And in fact, so a classical spin liquid, if we consider an Ising model for on a triangular lattice or a Kagome lattice, I mean, these can be solved, the statistics can be solved exactly. And one finds that there's an exponentially large number of states which have exactly the exact same ground state energy. So there isn't a full selection. And we also want low spin. Low spin really corresponds to the lightness there. We'll have more quantum fluctuations. Okay, next slide, please. Okay, so far we talked about just spin orientation. That's like a classical model. Okay, when we have this highly degenerate situation and we add quantum mechanics to it, then quantum mechanics will lead to superposition and entanglement. And that's where the possibility of a quantum spin liquid arises. So if we consider an Ising model which is highly degenerate, and we could add various types of transverse fields, which fields that do not commute with the Ising degrees of freedom. Okay, those will lead to quantum fluctuations and will lead to superposition of many states. Okay, so those could be of the type HISIX, like a transverse field term, or it could be a transverse exchange term where the XX terms, which can flip a pair of spins, for example. Okay, so we know that when such transverse terms are applied, for example, for just a Heisenberg coupling between two spins, then the ground state is actually a singlet, which is a linear superposition of the up-down and the down-up state. Okay, so the question is, if we have such a highly degenerate state in a macroscopic system, many possible ground state without considering quantum fluctuations, what would quantum fluctuations do? Okay, so one possibility is that the result could be a quantum spin liquid with a very high degree of quantum entanglement. Next slide, please. Okay, but really, most often what happens is that systems find other ways to lift the degeneracy. Okay, a very, very important early model, really exactly soluble model, was this model by Majumdar and Ghosh. Chanchal Majumdar's name I already mentioned. This is a model if you consider uh, a chain of spins with nearest neighbor and second neighbor interactions, which can also be written in terms of triangles like this. Imagine making triangles with equal interactions on every bond of the triangle. So this system is also highly frustrated and can be shown classically. It'll have many, many ground states. But when you apply quantum fluctuations to this model, instead of the ground state becoming a linear superposition, you end up with two degenerate ground states where spins simply form a singlet with one of their neighbors. So they're really two degenerate ground states in which we say that the system spontaneously dimerizes and develops valence bond order. Actually, later on, we'll come back to systems like this because that's where Bose condensation is really seen. But this is not a spin liquid. Another thing that can happen is what is generically called order by, in fact, all these can be generically called order by disorder. Actually, what could happen if you consider, for example, on a square lattice, a model where you have a nearest neighbor interaction, but a larger second neighbor interaction. So if the second neighbor interaction is large, then the second neighbors, they like to align anti-parallel. But then once the second neighbors align anti-parallel, basically they don't apply any field on the spins in the middle. So the two sublattices in some sense decouple, and they can orient in any arbitrary way. But one can show that in this model, if you allow for quantum fluctuations, then the fluctuations select a particular type of order in which all the spins lock in a collinear manner. So basically, fluctuations can help to remove the degeneracy and select a particular order. This is what happens very often. Instead of going into some kind of a quantum spin liquid phase, which we are most interested in, the systems often turn into basically some other kind of ordered system. Okay, next slide, please. Okay, so the quantum spin liquid will really is a hypothetical state. In my view, it still has not been definitively observed. We are still, in some sense, searching for a quantum spin liquid phase. It will be an emergent state of matter, not adiabatically connected to a product state. Okay, so basically the simple ordered states are in some sense perturbatively related to fixed spins on every site, or the Majumdar-Ghosh state basically is a product over pairs of spins. So an emergent state that basically the idea was first proposed by Phil Anderson, a highly resonating valence bond state. That means if you want to think in terms of spins pairing up with other spins to form singlets, then it's a linear superposition of many, many such pairs, exponentially large number of such valence bond systems, such that no spin has a definite partner, really. Okay, and of course, this idea took off when we were when high temperature superconductivity was discussed and became a very big subject. And more recently, there's been a lot of exactly soluble models, such as the Kitaev model, which shows that many of the things that we are talking about are actually true. So, in particular, they show the reason why quantum spin liquid states are so coveted is because they have very, very interesting properties. They show this property of fractionalization, that is basically the new kinds of degrees of freedoms can emerge, which are really like partons in particle physics. I mean, but they are emergent partons. They arise from these spins, but they could be like spinless fermions called spinons, or they could be some. So just to give you a simple example, if you imagine creating an excitation by breaking a pair of spins, then uh, these two objects over here, the triplet that one has created, the two excitations can separate and become an independent excitation in itself. Okay, so such things can be shown in theoretical models. Basically, they are not really free. They interact with each other via an emergent gauge theory. So these systems are also realizations of uh, quantum gauge field theories, and they have, of course, long-range entanglement. So there's a lot of interest in finding these systems. Okay, next slide, please. Okay, but experimental identification of such systems remains a huge challenge, has not been successfully done yet. The earliest important step really in this direction was taken by Art Ramirez, who introduced something called the frustration parameter. So the frustration parameter is the ratio of the ordering temperature to a mean field ordering temperature, or the Curie-Weiss temperature, which people are very familiar with in magnetic systems. So when the system doesn't order, when you lower the temperature by a factor of 10 or factor of 100 or factor of 1000 with respect to the expected ordering temperature, then we say that, okay, there is something, the system is highly frustrated, and perhaps this is a candidate for quantum spin liquid. Of course, by now, from a theoretical point of view, there are all kinds of really interesting smoking gun signatures that people have come up with that would nail down that, yes, you have found a really exciting quantum spin liquid phase. So one of them is a quantized response. The one system that I would say is very much like a quantum spin liquid is the fractional quantum Hall effect. I mean, it's not a spin system, but that we know there we have fractional charges, fractional statistics, and also we know it primarily from the fact that you have quantized Hall conductivity. But in a neutral system where we don't have charges, one has to look at some other kinds of quantized responses, for example, the quantized thermal Hall effect. And actually, there are some very interesting experimental claims that this thermal fractionally quantized thermal Hall effect has been seen in some materials, but I think it's still debated. In my view, it's not settled yet because the experiments have not been reproduced by more than one group. There are other very interesting claims, again from theorists primarily, that the thing that distinguishes a bosonic system from a fermionic system is that in bosonic systems, you typically have low energy excitations at one point or maybe 2 or 3 points in the Brillouin zone, whereas a fermionic system has a whole Fermi surface where you have low energy excitations. So there are many, we know from the behaviors of metals that there are lots of interesting quantum phenomena in metals, for example, quantum oscillations as a function of magnetic field. The question is, can you have quantum oscillations in insulators, which are not metallic, which have a spin-on Fermi surface, okay? And how would you observe them? Again, I would not go into this in more detail, and there are many experimental claims, but unverified in my view. I mean, and these examples would indeed be smoking gun signatures of a quantum spin liquid, but has not been established in my view. The thing that mostly people focus on first is really looking for a continuum in scattering measurements. Okay, that remains the most potent tool for going after quantum spin liquids in the absence of these really fancy but difficult experiments. So basically, the point is that when you have fractionalization, when your degrees of freedom are fractionalized, they actually, it's like your material is a universe in itself, which can support all these fractionalized particles, but these particles cannot talk to somebody outside. They cannot leave the system. They cannot talk to something outside. They have this behavior only as long as they are inside your system. And so the outside probes, whether it is neutrons or whether it is photons, they only couple, the external probes, they only couple to combination of these particles which are normal. So as a result, what happens is that if we look, for example, at the energy momentum relation, so if you look at the left side of the bottom plot, and these are taken from Leon Balance, basically plots made by him. So basically, the energy momentum relation is such that in a normal ordered magnet, there's a well-defined spin waves or magnons have well-defined energy momentum relation, and so it's kind of easy to measure experimentally. And once you know that, you can easily deduce what the Hamiltonian for such a system is, what are the exchange parameters, and so on. Whereas in a system that has fractionalized degrees of freedom, basically the neutrons will couple to a pair of spin-ons, okay, which will have the quantum numbers of a neutron. And so in that case, basically for any given momentum, you don't have a definite energy, you have a range of energies. Okay, so people look for this kind of continuum, but it really requires detailed theory in order to make sense of the experiments and to deduce, what kind of Hamiltonian are we talking about. So next slide, please. Okay, so then the next question is, what is the right system? Where should one look for such quantum spin liquids? So the early focus obviously was on spin half systems and low dimensional transition metals. So basically, mostly people focused on copper-based materials. The Herbert-Smithites, which are Kagome antiferromagnets, have been a big focus of attention. But an alternative really is to study these rare earth-based magnets. Okay, so basically these lanthanides, and in spite of having a large angular momentum, total angular momentum J, one can actually have, with spin orbit coupling and crystal fields, essentially low-lying doublets for each. Let's take this example of ytterbium, which is one of the most popular one, and there's a statement from Kate Ross that ytterbium is the new copper. In this particular ionic state, it has L equals 3 and S equal to half, giving us J equal to 7/2. But it forms, this, you can see this has an odd number of electrons in it. So this is a Cramer's ion. So every energy level of a particular atom has to be doubly degenerate. And the low-lying states is usually a doublet, which is often well separated from other other atomic states. So to a very good approximation, it acts as an effective spin half system. Okay, so one can look for interesting quantum phenomena in such a system. So next slide, please. Okay, so there was a long introduction to quantum spin liquids. Basically, the rare earths have been most popular for really studying these systems called spin ice. So the ice, which is really the solid phase of water we are all very familiar with, is a highly hydrogen bonded system. To 0th order, this is a molecular crystal of water. If we ignore the protons, basically, which are tiny objects compared to the oxygen ions, basically the solid circles are the oxygen ions. The oxygen ions form a four-fold coordinated lattice, very much like the silicon or diamond lattice. So each oxygen has 4 neighboring oxygens, but there's twice as many protons as there are oxygens here. So there's essentially a proton on every bond. Okay, so there are twice as many bonds in this lattice as there are sites. So and very early in studying such crystals, people came up with these ice rules, which basically says that while there are these 4 bonds over here, if you look at any oxygen, there will be 2 protons near it and 2 protons far away. In other words, 2 protons are like chemically bonded, and the other 2 are only hydrogen bonded to this particular one over here. But such ice rules lead to many more ways in which these protons can arrange themselves. And very soon it was realized that you can have spin systems. Okay, I think this originally was again due to Phil Anderson. If you have a lattice of corner sharing tetrahedron, imagine that you have a lattice of corner sharing tetrahedron, and the spins sit on the vertices of these tetrahedra, and basically they orient either towards the center of one tetrahedra or the center of the other tetrahedra. Then uh, and imagine in addition that the interactions between the neighbors is such that if one spin points out of the tetrahedra, the neighbor wants to point in. Then this system basically is exactly like the ice system. That's why it's called spin ice. You can think of the center of the tetrahedron as the location of the oxygen, and you can think of the spins basically as if they are like the protons here. And when the spin is aligned one way, it's like the proton is away from that oxygen, and when the spin is pointing in the other direction, it's like it's close to that. Okay, so actually such systems uh, basically will obey the ice rules, okay, on such corner sharing tetrahedron. So next slide, please. And indeed, such pyrochlore-based rare earth magnets were discovered uh, basically by Art Ramirez and collaborators somewhere around 1999 or so. So Linus Pauling basically showed that the degeneracy associated with the ice rules is exponentially large. Okay, and basically he had a very simple argument how to count how many configurations are there that obey ice rules, and basically you can come up with the count in this very simple way: 2 to the power n, if we think about each spin as having 2 configurations, then the 2 to the power n configurations if there were no constraint at all. But then if each tetrahedron uh, independently occupies a constraint, then for each tetrahedron we know only 6 out of 16. It has only, if the ground state is one where 2 must be in and 2 must be out, there are 6 ground states. So 6 out of the 16 possible states of these 4 spins that's the constraint due to each tetrahedron. And since there are n over 2 tetrahedra in the system, the total configuration must be 2 to the power n divided by 6 over 16 to the power n over 2. And it's actually, Jan Oitma and I tried to study this by much more very high order series expansion. This result is extremely accurate. It's accurate to basically a few percent. So anyway, Art Ramirez and collaborators, what they did was they measured the heat capacity of this material, let's say in zero field. And if you integrate from low temperature, you find that basically it doesn't give you the full R log 2 entropy that you expect between zero and high temperature for a two-state system. Instead, there's a deficit in entropy, which is exactly given by the Pauling entropy. So this was a nice demonstration of a spin ice phase. Next talk, please. Okay, so this subject really became exploded, became of great interest really when Castelnuovo, Mosner, and Sondi, they brought up the idea of monopole excitations in the system. Basically, when you flip a spin, it creates a spin dipole, if you like. It creates 2 poles over here. One, if you like, it's like there's a north pole and a south pole, but you can keep on flipping neighboring tetrahedra without any extra cost of energy. And at the end of the day, you'll end up with 2 well-separated monopoles, essentially. So this is an example of an emergent, this is at a classical level, because we haven't talked about any quantum fluctuation. It's about it's an emergent classical system that it's highly degenerate, that leads to fluctuating magnetic field that continue to satisfy this magnetostatic relation, that divergence of B is equal to 0. Okay, but this is a nice example of a classical spin liquid, and indeed it has been observed in many experiments. Okay, next slide, please. Okay, so now what happens if we add quantum fluctuations to this? So this depends on what kind of quantum fluctuation. The type that is kind of easy to theoretically see what it does is basically a transverse exchange like this. So if you add to this Ising term, which is the second term, the transverse exchange like this, basically this, every time you have an up-down spin, it can be flipped by such a term. So one can show that if you add such a term to this, then in second order perturbation theory, nothing happens, that every state's energy is shifted by exactly the same amount. So in second order perturbation theory, there is no selection, or there's no lifting of the degeneracy. But in third order perturbation theory, something very interesting happens. So if you imagine, so in this pyrochlore lattice, basically you have many hexagons like this, because if you look along certain directions, you'll find Kagome planes which have lots of hexagons. And what is drawn over here are 6 tetrahedra, which are arranged in this hexagonal fashion over here. Okay, alternately the tetrahedra point up or down. So you can imagine a spin configuration in which the spins are arranged in such a way that over the hexagon, they basically go around in a circle like this. So if you look at any one hexagon, there is one of these guys which is pointing in, and the other guy is pointing out. And the other 2 spins which are not shown in the picture, they obviously also must be one pointing in and one pointing out. So basically, in the third order perturbation theory, what this kind of a term can do is each order it can flip a pair of spins. So in the third order, it can flip all 6 of the spins. But what you see is that if you flip all 6 of the spins, you basically go into a configuration in which the ice rule is still maintained. Okay, so because in every tetrahedron, you still have 2 in and 2 out. You haven't changed the number of in and out spin in any of the tetrahedra. So basically, in third order perturbation theory, the way the degenerate subspace is the way the effective Hamiltonian that we get in our degenerate subspace is not that one state is lower in energy than the other, but rather there's a resonance. You start to resonate between this configuration and this configuration. And of course, the lattice is full of such hexagons all over the place, and it still requires more theory and computational work basically to show that these resonances actually stabilize an emergent spin liquid phase. It's actually a quantum electrodynamic phase, because it's a phase that has emergent electric and magnetic fields which can fluctuate in the absence of any charges, because charges are all gapped out. There's an energy cost for them. But at low energies, you can still have a photon mode, okay, which is entirely made out of these spin degrees of freedom. So there's the emergent photon, there's an emergent quantum electrodynamics in this system. Okay, so obviously there's a lot of interest. Is such a mode realized, such a state realized in pyrochlore materials, and if so, in which ones? Okay, next slide, please. Okay, so basically, I think I'm going to skip over some of these slides over here and just say that, you know, there's been a lot of interest in these kinds of systems, but unfortunately, so far, the systems seem to escape the quantum spin liquid behavior. Okay, the systems that have been studied in detail, they actually end up ordering in one way or another. Okay, so next slide, please. Okay, so yeah, so one thing that is really nice about the spin ice systems is that you know, the energy scale is very small. And the small energy scale means that one can saturate the spins system by applying a field. Okay, so in low field, we don't even know what the it's not easy to even figure out what are the exchange interactions in the system. But if you apply no matter how complex your state is, how exotic the state is at low magnetic fields, when you apply a high enough magnetic field, the spins will all be saturated, and then the excitations will be simple. And from those excitations, you can basically deduce what the exchange parameters are. Okay, next slide. So I'm going to skip the details of this particular system, because at the end of the day, the message is that the system does not does not remain a spin liquid. At the end, there is some selection mechanism, and the system ends up ordering due to the disorder. Okay, next slide, please. Okay, yeah, but the thing that makes these rare earth systems very interesting, of course, is that you have huge possibilities. Okay, many different combination of just for example, in this A2B207 systems, where A can be many of the rare earths or even some of the non-rare earths, and B can be many of the transition metals, and even some other systems are possible here. And so there's still a lot of optimism that perhaps a quantum spin liquid would be found in these systems. Okay, next slide, please. Okay, so I'm going to change directions and say a little bit about spins and bosons. Okay, well, let's go to the next slide. Let me just focus. Let me go straight to the particular material. So I'm assuming that people are very familiar with the theory of Bose-Einstein condensation in an ideal Bose gas. Okay, next slide, please. Okay, so here's the system that we studied recently, and it's based on some experimental work by Kate Ross and collaborators on a particular system, which is also in this 227 stoichiometry, basically, which has this property that you have two spins which are coupled much strongly. The J intra is a much stronger coupling than the J inter. In fact, from various measurements, one knows that the J inter is about 3 times weaker than the J intra, and that's because the distances are different. Okay, so in such a system, basically the ground state is very simple. In zero magnetic field, the ground state is a dimerized system. It's much simpler than the Majumdar-Ghosh model, basically because this is not a spontaneous dimerization, but it's really just from the crystal structure that two spins happen to be close to each other, and they form a nice singlet state. And then basically, as you apply a magnetic field, that changes each one of these dimers, if you like, the ground state is a singlet, and it has 3 excited states, which are triplets. And when you apply a magnetic field, basically these triplet excitations, which act as bosons, can at some stage post condense, and then they go into some kind of magnetically ordered phase. And again, if the field becomes too strong, then the spins again polarize along the field. Okay, actually, next slide, please. Next slide will kind of show the general idea here. So imagine, so basically what happens, and this is taken from this review article by Giamarchi and collaborators. So think about the single particle energy levels as a function of K. Okay, so once you have some, if we just had isolated dimers, then all the triplets will have exactly the same energy. And when you apply a magnetic field, the magnetic field just acts as a chemical potential. It just changes the energy of each one of these. It doesn't change the states at all. And in the absence of any interdimer couplings, each one of these states, basically the S equals 0 state will be unaffected by the magnetic field. The S equals +1 state will go down in energy, -1 will go up in energy, and there will be some magnetic field at which the triplet state will actually become lower in energy, and at that stage the ground state will simply flip from the singlet to all the spins in the triplet state. But once you have a coupling between the dimers, then there's a dispersion. There's going to be an energy dispersion for these triplet excitations, and then there'll be a Bose condensation at the bottom of the triplet. basically. So at some HC1, there will be a Bose condensation. And then at HC2, basically, that is where, after which the system will go into a saturated state. So in between, there's a Bose-Einstein condensation dome, which is really an ordered antiferromagnet in the XY plane. Okay, next slide, please. So again, there are a lot of experimental systems where such Bose-Einstein condensation has been measured. Okay, so basically, most of these are, as you can see, transition metal-based metallic systems. But typically, you can see that most of the cases, the experimental data doesn't go all the way up to the saturation magnetic field, because one needs something like 60 Tesla or 50 Tesla field in order to do that. Okay, next slide, please. Okay, so this particular system, terbium silicon oxide, this was studied in these two papers basically by Kate Ross's group. Okay, next slide, please. So this system, first of all, so here's the measurement, the experimental, the zero field specific heat can be basically well fit by a system of weakly coupled Heisenberg dimers, as you can see from this fit over here. Okay, next slide, please. But the nice thing about this system, of course, is that the saturation field is only about 1.5 Tesla. So it's relatively easy to generate experimentally. And on the left side is shown the specific heat data as a function of temperature as you increase the magnetic field. So the lower data is the one that I showed earlier, basically, which corresponds to zero magnetic field. Now, as you apply a magnetic field beyond this HC1, you see the sharp phase transition over here. That gives you this boundary. And basically, by following the maxima over here, one can get this Bose-Einstein condensation dome. Okay, next slide, please. There are other ways to confirm this phase diagram. For example, one can do ultrasound measurement, ultrasound velocity measurement. And this, of course, depends on the stiffness of the system. Again, that depends on the kind of phase that one is in. And if one looks at this measurement, basically, one can infer where the behavior changes at HC1, HM, and HC2. And actually, this is indirectly measuring the magnetic phases, but one can also see that on the right side, basically this curve is flipped over and is compared with the squares over here, which are basically nothing but the derivative of the neutron scattering Bragg intensity with the magnetic field. And so pretty much tracks the magnetic behavior over here. So one can infer the HC1, HC2, and HM that I discussed before from these kinds of measurements as well. So next slide, please. In addition, Kate Ross's group has also measured the neutron scattering, inelastic neutron scattering, in which you can measure the dispersion, which in zero magnetic field basically gives you a gap system. Okay, there's an energy gap. And when one goes past the HC1, then there's a region, you can see there's a second mode that comes up, which seems to be a quasi-Goldstone mode. I mean, we believe that ultimately there is a gap in the system, but the gap is very small. At least within the measurements, it's consistent with having no gap. And then again, when you go above HC2, you again get some kind of a gapped system. Okay, next slide, please. Okay, so there's a certain mystery, and this is basically what we were trying to explain over here. So this system has a difference. There's what is this H sub m in the middle over here, and why is there an asymmetry in the behavior? So if you look at the heat capacity over here, on the left side of H sub m, there's a sharp phase transition, as you can see from the sharp kink in the behavior. Whereas when you go to the right side over here, as you can see in the top two curves, you don't see that sharp. It's almost like you can get into this phase without any crossovers. Okay, as a crossover without any phase transition. Okay, so the character of the excitations also changes at this point H sub m. So various measurements basically show that there's as if there are two different phases inside the dome. So what's new over here? Why do we have this? So next slide, please. So this is basically what our work was trying to address. So if you just have a Heisenberg model that already gives you qualitatively most of the to 0th order all the details, but it doesn't give you this H sub m and the reason for two phases. So you need to introduce some anisotropy in order to have two phases in there. And what we found was that the only way to you need actually two forms of anisotropy. You need the coupling in the xy plane to be anisotropic, and indeed there's no reason a priori from the crystal structure that the coupling along x and the y should be the same. So we need a weak anisotropy between the coupling along x and the y. But we also know that y is the only axis of symmetry over here. So the this tensor over here, this gyro, this g factor over here, when the magnetic field is applied along z, it not only affects the spin along the z-axis, but also along the x-axis. So gzx does not have to be 0. Okay, only zy has to be 0 by symmetry. So these two factors together can give us a phase boundary that looks something like this. Basically, there's a singlet phase at low magnetic fields, and then there's a phase on the left over here in which there is a in which the spins order along the y-axis, which is the only direction in which there is no field, really, the only component of spins that feel no field. So that's a spontaneous order. But then that goes to 0 at H sub m. But the spins continue to point basically along the x direction, and they saturate along the z direction. At really high fields, basically they'll saturate mostly along the z direction and very small along the x direction if the anisotropy along x is very small. So basically this is the kind of behavior that one can get. We studied it using DMRG, dynamo mean field theory, spin wave theory, etc., by a variety of theoretical methods. Okay, next slide, please. And among other properties, basically one can quantitatively reproduce various aspects of the experiment. For example, by measuring the derivative of the mz square with respect to h, one can basically get an explanation for the ultrasound measurement. Okay, so next slide, please. Okay, so let me not go into too much detail on this. Basically, the point of was that when you look at the model in detail, there's only a very small parameter region where one obtains this kind of behavior. If you make either kind of anisotropy too small, then basically either the y-ordered phase covers the entire range or it disappears entirely. Okay, so next slide, please. Okay, so let me come to the summary of my talk. So basically, rare earth magnetic systems provide a platform for many types of exotic spin states. Strong spin orbit coupling and crystal fields lead to doublets, which act as spin half degrees of freedom. And SU2 symmetry, of course, is broken by anisotropic terms here. And small exchange energy scale allows exploration of the behavior from zero field to saturation. That's one of the real advantage of the rare earth systems. And there's a huge variety of rare earth based systems, okay, that allows studies of many facets of frustrated quantum magnetism. And it remains one of the most active areas of research in the quest to find quantum spin liquids, a phase of matter that people are very interested in, but have not yet successfully found. Thank you.
Thank you, Professor Singh, for such a wonderful talk. Now the talk is open for the question, comments. Okay, so I may not be able to see everyone's raised hand because somehow it's not showing. So please, if I'm not able to tell, Seti, please go ahead.
Okay, thank you. Professor Singh, thank you for the talk. It was really informative. I have one question or something like a bit out of this, but taking concept from your Bose-Einstein condensation. So if we perform Ortus measurements on lithium iron arsenide, for example, it's a superconductor, there instead of seeing like at the Fermi level rather than a kind of curvature, what we see like a shift down of the band just below the Fermi level. So how this Bose-Einstein condensation?
I'm sorry, I'm not able to understand your question. Sorry, can you repeat it again?
I think you are aware of this Bose-Einstein condensation discussion in superconductor lithium iron arsenide.
Yes, I mean, so that's a kind of Bose condensation also, yes.
Exactly. So there, instead of like curvature just below the Fermi level, I mean, in below TC, the band should bend down, right? I mean, bend down below TC at the Fermi level. But rather than bending down the band, the whole band shifts just like below the Fermi level, like a flat band. I just want to understand what's happening exactly there. I don't know whether my question was clear.
Yeah, but I'm sorry, I'm not. I will not be able to answer that question.
Okay.
Not sufficiently familiar with the bands, the behavior of the bands in a superconductor. Okay, I see Bhaskaran is there. Maybe he knows how to answer that question.
Sorry, I haven't understood it carefully, so I will think about it.
Okay.
That's a nice question.
Thank you very much. Yeah.
Yeah, Professor Bhaskaran.
Yeah. So Rajiv, very nice talk. After a long time, we are meeting each other in the two-dimensional world. So I enjoyed your talk, and I have a question about this connection of triplet condensation in dimer system and to the magnetization plateau. For example, even if you take Majumdar-Ghosh model or Shastri-Sutherland model, which are dimer systems, when you apply strong magnetic field, there is a magnetization plateau, which is often a quantum spin liquid, like a spin-on condensation. So, does that, like, when your Bose-Einstein condensation density increase, is there a possibility that you will get the quantum spin liquid rather than a Bose-Einstein condensation?
So now you are asking the question, if my system was frustrated,
yeah,
that's a possibility, yes. Yeah. This particular system is not. I mean, this is a
not frustrated, I see.
This one is really on a honeycomb lattice and is not frustrated in that sense. But that's a good point. Yeah, that the Bose condensation can lead to plateaus. They could happen for classical reasons also.
Correct.
Those can also happen because they like to order in such a way that they form a crystal. But they could also go into. There are examples where they could go into a quantum spin liquid phase.
Yeah. Thank you, Rajiv. Yeah, very nice.
Thank you.
Okay, Brijesh Bhaiya.
Thanks, Professor Rajiv Singh. This is Brijesh. Nice talk. I have a question about your last, this system on honeycomb, sort of system with BEC and so on. The question is the particular model, the anisotropies and the local ion I mean, these G, anisotropic G that you see, I mean, is it sort of substantiated by, I mean, the necessity for this is
No, so
substantiated by experiments or
yeah,
not?
very good question. Yeah, so I actually I think my slides that I sent to Manoranjan was actually the slightly older version. I emailed the incorrect version there. Yeah, I did have something. So there's still things to be checked by experiments. In particular, so of course the G factor is so small that is not what I would say one should measure directly, but one can directly measure two things that would be a good verification of our theory. One is we predict that left of the HM, the system should order along the y-axis, and then on the right it should be mostly in the x, and of course z is constantly increasing as well. So that is a very clear prediction, and in particular NMR type experiment should be able to show that. But we have a second prediction which is very specific to our model, really. That is, so because we don't have XY symmetry, so that means we don't really have Goldstone mode. So, if you're really dealing with a Heisenberg system, then once you go into the ordered phase, you must have a true Goldstone mode, which would have an energy, which will not have an energy gap, right? So the energy of the excitations will go to zero. The neutron scattering actually has a very large error bar, actually. I mean, they have a very big resolution. They cannot tell that there's a gap less than something like 17% of the weaker exchange. So that's a very large amount. But so our prediction would be that there should be a gap, it should be small, but that gap goes to zero precisely at HM and then opens again on the other side.
That's right.
So that's very specific prediction. But yes. So until those things are tested, I would not say that our theory is necessarily correct.
Okay. And just one more question, if Manoranjan may allow, or more like discussion. So, I mean, as you said in the introductory part of your talk, long-range quantum entanglement is sort of one sort of desires to realize quantum SpinLiquid states. But I'm saying, isn't it also a bit of the counter sort of to the very expectation? Because even in Nell order has long range I mean, what I'm saying is
it's not long range entanglement.
What I mean to
Nell
say
order
is,
is not.
Just let me sorry to interrupt, but just to what I mean to say is when you have very long range valence bonds, by entanglement I mean typically we think about singlets being formed and so on. So if a long range entanglement exists, then there is a long range longer sort of valence bonds that exist, but then they eventually tend to lead to order and not to so what I'm saying is long range RVB is not necessarily a SpinLiquid. That is what I mean to say.
Not
so what is your thought on that?
I agree with you on that. So in some contexts, for some certain types of models, there are precise definitions of what long-range entanglement means. In certain gap systems, one can define this has been done by Kitaev and Preskill and by Wen and his student, basically, that you can have a precise definition of long range or topological entanglement. Okay, so I didn't give a precise definition of entanglement anyway, but most of these systems, the entanglement really comes from neighbors. Entanglement in many body systems, at least in spin systems, not in fermion systems, spin systems is usually local. Okay, it's neighbors. You mostly entangle with the neighbors, or maybe second neighbor or something like that. So entanglement usually obeys an area law. But these kinds of systems, when they have new kinds of topological order, they show something which is very long range. So there is a precise definition of how one can theoretically calculate such an entanglement. I don't think those things can be measured really. But so you are right. I mean, the RVB description actually, now there was a famous paper, which again Bhaskaran would remember, the Liang, Dussault and Anderson paper that showed exactly what you are talking about, that, you know, when you have very long range singlets, that kind of a system essentially turns into a Néel ordered system.
Yeah, that was the sort of
Yeah.
dilemma I had, that what precisely one means.
So, if I may make a comment,
Yes.
so what Brijesh is telling is about the content of the RVB state, namely long range entanglement between two spins.
Right.
Yeah.
The kind of thing that Rajiv is telling, for example, it happens in Kitaev model, that is, it's beyond area law. There is a constant which is called quantum dimension. That comes from very different reasons altogether. The objects that are entangled are no more individual spins. So it is some collective objects which are entangled, which leads to what is called quantum dimension or topological order. So one goes beyond the elementary constituent entanglement.
Right. Yeah.
So you are saying this is not entanglement of the physical spin, but of these new emergent variables. Is that
Exactly? Yeah. That's what I'm saying. Yeah. In fact, it can be made more precise if one thinks about Kitaev model, even in one-dimensional, Kitaev model. It can be made. There are some interesting discussions.
In fact, in the interest of this very interesting question, and for everyone else, I had another question related to the same discussion. I mean, is it, for example, it brings us to the question of fractionalization and these emergent degrees of freedom, which of course is manifestly there in many theoretical and also experimental situations. But I mean, is it necessary to have those things to realize a spin liquid? For example, the high temperature paramagnet is a spin liquid, and it doesn't, one doesn't need any of that.
No,
I'm not saying, yes,
yeah,
please.
That's definitely not a quantum spin liquid, and I would not call it a spin liquid either. I mean, that's what I was trying to explain in the beginning. Certainly a quantum paramagnet is not a spin liquid, because in some sense it's perturbatively related to independently fluctuating spins. Or perturbatively related to small clusters of independently fluctuating spins.
Like dimers and so on.
Exactly.
Okay, so yeah, one has to sort of understand what spin liquid is in somewhat more very clear terms, not just by analogy. Yeah.
In the context of quantum, Kitaev model, there are these topological excitations, Majorana fermions and Plaquet excitations. And some of these quantum dimensions and long-range entanglement can be understood in terms of those emergent degrees of freedom. So even though the constituent degrees of freedoms are spin. So I just wanted to ask a related question to Rajiv. Rajiv, you mentioned that yours is not a frustrated system because it's a honeycomb lattice. So while there is no geometric frustration, you indicated there could be magnetic anisotropy.
Yes.
So that could bring, like in Kitaev model, frustration in spin space. So I do not know about the magnitudes of the corrections that you are talking about, whether there is an interesting possibility that what you think as a triplon spin liquid has some content of, this. I do not know. I'm just loudly thinking.
Actually, we were also trying to put in Kitaev interactions into this calculation, but we were not able to reproduce the experimental. That doesn't mean that there isn't one.
Okay.
We were only able to reproduce the experimental behavior with very, very weak anisotropy.
Anisotropy, okay.
Less than 1%. Really weak anisotropy. And the moment you make it strong, it kind of deviates strongly from what the experiments see.
And also, as a model system, it would be very interesting to start with your model where the dimers are there by hand, and then include some frustration and see how Bose condensed triplon become a spin liquid. That will be interesting.
Any other question? If there's no other question, I have one simple question. So, I was just wondering that what is the criteria for this condensation in the magnetic system? Theoretically, how we see that? Okay, this is the condensation of the like magnons.
So basically, one should think of. Let's think of a Heisenberg system, because the system which has SU2 symmetry, that is the cleanest. So in that sense, the magnetic field doesn't change the states of the system, right? All it does is it shifts the energies, right?
Yeah.
So in that sense, it really acts like a chemical potential, right? So when you are in the singlet state, the state in zero field or low field is some kind of a singlet state, basically, right? Because think of individual dimers, if you like, and on each dimer you basically have a singlet ground state. And then, of course, even if they are coupled, it's some weakly perturbed version of that singlet state is your ground state in zero field. Okay, and then above that you have these triplon excitations, right? Which come in three varieties. There's the spin up type, spin zero type, and spin down type. So when you apply a magnetic field, you're lowering the chemical potential for the spin up triplon. The other two are not so relevant here. So the spin up triplon, the chemical potential at the beginning, the chemical potential is way below where their energy levels are. And so in the ground state, they are simply, none of them are present. But at some stage, the chemical potential keeps on getting closer and closer to the bottom of the band as you increase the magnetic field. And at some stage, it touches. And the system is always so the thing about this particular example of Bose condensation is that this is really very close to an ideal gas Bose condensation. It's not like superfluidity, which is a very highly, strongly interacting system, really, because when you are close to this HC1 point, I'm not talking about in the middle of the Bose condensed dome, near the HC1 point, basically the system is extremely dilute. There are very, very few triplons present in the system. And the behavior is quantitatively very close to that of an ideal Bose gas.
Okay. Why I asked this question, because the multipolar phases, what we see is, there is even for very small change, there are lots of magnon condensate. And then in MH curve, we see there is a sharp jumps. Here I was seeing the linear behavior. So that's what was...
Linear behavior in what?
In MH curve, there was a linear behavior, isn't it? In magnetization and magnetic field, even in the condensation region, it was varying almost linear.
Not right at HC1. It should be linear. At HC1, from zero, it should
be jumping.
Yeah.
Okay.
So if I may make a comment.
Yeah, please.
It's a very interesting discussion. In the case of Rajiv's example, the triplons are tightly bound to spin-ons. They are really, there is no spin-on content essentially. Whereas if you go to Majumdar-Ghosh, the excitations are like, you can say, two weakly interacting spin-ons. So, so it's like, in Rajiv's case, it's like a point boson. It's like a lattice boson.
Mm-hmm.
Whereas in other models, like Majumdar-Ghosh or Shastri-Sutherland, this triplon has structure. It's very fat. So they start interacting and you have quantum SpinLiquid behavior. Am I right, Rajiv?
Yes, and the Shastri-Sutherland has been studied a lot.
Yeah.
There's a very nice experimental example of the Shastri-Sutherland example, which is a two-dimensional version, if you like, of the Majumdar-Ghosh model.
Right.
Yeah, and that one really has a very, very rich Bose condensation and maybe more fancy spin liquid behavior in a magnetic field. Yeah, that's a very interesting system.
Yeah, currently we are also studying this Sastry-Sutherland model, but it's anisotropic. And there we have a ferromagnetic dust along the squares and antiferromagnetic along the diagonal direction. And that has lots of interesting features. And especially, I think there is some kind of condensation and things like that there. So still, like, sorry?
Which experiment, which material is this?
Well, this is not experiment. It is just a theoretical thing.
Just theoretical model.
Yeah. Yeah. So, yeah, but experimentally, I think there was one compound. It's some copper oxide. But I think there is still confusion whether this is really a B.S. Sastry model, anisotropic B.S. Sastry model, or Sastry-Sutherland model or not. So, yeah, thank you very much.